Hi, today we're going to be looking at edge finding, and we're going to be looking at 4 different methods. The first is edge finding by touch. The second, edge finding with an edge finder. Then we're going to look at edge finding with a dial indicator. And finally, edge finding with an edge finding square. We use edge finding to position the axis of our mill directly above a reference surface. And if we do it in 2 separate planes, well, we can place our axis directly above a reference point or a reference corner on our part. But one thing's for sure, using edge finding to accurately position the axis of our milling machine is really not useful if the head on the mill isn't properly trued up. So let's look at truing the head of a milling machine. Most vertical milling machines have 2 adjustments on the head. The first is the pitch adjustment, and that's controlled in this case by these 3 screws here. And the second is the yaw adjustment, and that's controlled with the 4 screws at the front. It's important to note that the pitch adjustment has a center of rotation that's far behind the axis of the milling machine, whereas the yaw adjustment has an axis that's in line with the spindle of the milling machine, and it's controlled by these 4 screws here. And we're going to verify the trueness of the spindle of this milling machine with a dial indicator that's just going to lick the surface of the table. It's mounted on a shaft and offset so that we can reach both ends of the table. 2 words of advice before we start. The first is really lick the table. Position your dial indicator so that it just skims the table by a few thousandths of an inch. That way, when you rotate your dial, you're not going to hit the edge of each slot. You're just going to skim onto each flat surface. The second word of advice would be don't try and adjust both the pitch and the yaw at the same time. Do one, then do the other, and then come back to the first one for a final adjustment. You're going to start with a visual adjustment using the scales that are indicated on each of the movable axes here. So the scale on the pitch and the scale on the yaw, set them to 0 as well as possible. Then I strongly suggest that you adjust the yaw first. And for that, you're going to choose a spot on the table. In my case, I'm going to use the very edge of this center T-slot to measure on one side and then rotate over 180 degrees and re-verify the edge of that same slot, the same edge on the same slot, on the other side of the axis of the spindle. Once the yaw is adjusted to within 1/1000th of an inch at those 2 points, we can start to think about the pitch. Now the pitch is a lot more complicated to adjust because its center of rotation is far back from the axis of the milling machine. And that means that when I pitch down on the front edge of the table, the back edge of the table is also pitching down, just at a slower rate. And that means that it's a little more complex. You really have to play with it to get it where you want. But where you want it is 0 at the front and 0 at the back, or at least well within 1/1000th of an inch. Once you've adjusted the pitch, it's not a bad idea to come back and take a look at the yaw one last time to make sure everything's good. And actually at the very end, you can go full circle and verify that you have no deviation greater than 1/1000th of an inch. At that point, your head is properly aligned, because if we have less than 1/1000th of deviation on 10 inches of sweep of that indicator, that means that a 1/2 inch or a 3/4 inch tool will have almost no deviation on it. Okay, so the head on my mill is nice and true. I've installed a milling machine vise and aligned it quite well, because obviously if we're edge finding and we have a crooked vise, there's no use for that. And I'm going to install a part, or I have installed a part, which is a 1, 2, 3 block, and it's already hardened and it's quite accurate, so it'll be a good candidate for edge finding. And since it's hardened, we can't use the touch off with the tool method because we don't want to damage the part or the tool. So we're going to use the touch off with a dowel pin, and I have here a 1/4 inch dowel pin that I'm going to use to touch off the part, but I'm not going to actually physically touch the part because I'm going to use a thickness gauge, 10,000ths of an inch, 15,000ths of an inch, whatever you're comfortable with, to install between the dowel and the part as I'm touching off. I've mounted my dowel pin in the drill chuck, and I've positioned it close to, but without touching the part. I've chosen a 10,000ths of an inch shim to evaluate by pressure or by friction how close the dowel pin is to the part that I'm trying to edge find. So I'm going to bring my dowel pin a little closer to the edge of the part, and using my 10,000ths of an inch shim and friction, I'm going to evaluate the proximity of that dowel pin to the edge of my part. I can see here that I have just a light or a very small amount of pressure. That indicates that my dowel pin is situated at 10,000ths of an inch from the edge of my part. It's important at this point to set our readout to 0 because this is only the start point of our edge finding operation. Since we touched off in X, we're going to set the X-axis to 0 here. If you don't have a readout, don't worry. You can use a micrometric collar on your lead screw just as well. Just remember, don't back up. In order to clear the part, I can raise the tool or lower the table. Once the part is clear, I can move my table in the X-axis by half the diameter of my dowel pin plus the thickness of my shim, which was 10,000ths of an inch. So 125,000ths of an inch plus 10,000ths of an inch equals 135,000ths of an inch. And that positions the axis of rotation, or the center of my dowel pin, directly above the surface that I'm trying to find. The last thing that I need to do will be to reset my axis to 0. That positioning is done. I can now move over to the y-axis. But this time we'll do it in one foul swoop to get a feel for what it looks like in real time. So I position my dowel pin close to the part, and I'll lower my spindle. So I'm now close to interference. I'm going to use my 10,000ths of an inch shim to evaluate the proximity of my dowel pin to the edge that I want to find, this time in the y-axis. Slight pressure right there, that's good. I'm going to raise my dowel pin and set my digital readout to 0, but this time in my y-axis. I can now move the table by 135,000ths of an inch, which is half of my dowel pin plus that 10,000ths of an inch shim stock. So there's 135,000ths of an inch. And finally, reset my y-axis to 0. So now I can physically move the table back to the original 0, 0 without resetting the readout here. I'm just going back to the X0 I'd found earlier, and I'm returning to my Y0, the one that I've just found. And there's my Y0. Now I can lower the dowel pin or the spindle to bring it close to the part, and I can see that I really am above the corner of my part. So there you go. We have performed a edge finding operation in X and Y by touch using a 1/4 inch dowel pin and a piece of shim. Now we've found the X and the Y, so we have a reference point from which to start our operations. And now let's take a look at the tool that most people consider to be the edge finder.
This type of edge finder is spring-loaded, so the head is free-floating. The end of this tool will gradually become more and more concentric as it approaches the side of the part, but will misalign itself rapidly as soon as it reaches full contact. This is not a cutting tool, but it is a rotary tool that we're going to use at about 800 RPM. It's very important to remember that the working end of this edge finder measures 200 thousandths of an inch. So now we can install the edge finder in a drill chuck, tighten it down well, and bring the working end of the edge finder close to, but without touching, the surface that we want to find. So since the head of this edge finder is floating, I want to purposely set it off center. Once I've turned on the spindle, we will see that as we get the edge finder closer to the part, the working tip will become more and more concentric to the tool's body, and eventually it'll be very concentric. Once the working tip is completely concentric with the body of the tool, that is when all of a sudden it's going to misalign itself rapidly. It's at that very point, once it misaligns, that I know that the edge of this edge finder is equal to the edge of my part. Once I've found my edge, I'm going to retract the spindle and advance the tool by half the diameter of its working end, which is 100 thousandths of an inch. At that point, my tool will be directly above the edge of the part that I'm looking for. So we have a very light contact, we're just barely touching, it's becoming concentric, and there we have our misalignment. Let's start over just to make sure. Very light contact, we're becoming more and more concentric, we're almost there, and there's our misalignment. So I can now retract the tool and turn off the spindle. We've just found the edge of our part in the x-axis, but we haven't positioned ourselves on 0 yet, so I'm going to set my x-axis to 0 and then move my table by half the diameter of the working end of that edge finder, and that's 100 thousandths of an inch. So there's my 100 thousandths, and don't forget, that is my new 0 above that surface. My axis is directly above, so I'm going to reset that axis to 0, and that's my x0. So that was x. Now let's take a look at y in real time. So let's start the spindle and bring the edge finder down to the level I need for it to work properly. So I bring the edge finder closer to the surface using the y-axis. I'm getting closer and closer, it's more and more concentric. Once it's concentric, there it is, I have my misalignment, and I can pull my tool back up, set my y-axis to 0, and then advance the y-axis by 100 thousandths of an inch, and that will position the center of my axis directly above the y-axis, and that's my y0. I will now physically return to 0, 0 by moving the tables. I'm not going to reset my readout here because it is set at 0. Then I'll be able to verify if I truly am above my reference point, or if you prefer, my reference corner. Once on 0, 0, I can see that the axis of my spindle is truly above my corner. So I've found my reference 0.
So those two first techniques, well, they're quite similar. Basically, the edge finder makes the job a little easier and a little quicker. But as far as precision goes, it's pretty well equal. But however, there are times when we don't want to work from the edge of the part, but that we'd rather work from the center of the part. And if that's the case, well, that's even simpler, because we're going to edge find the ends of the part and come back to its center. And that's really quickly to do, because over dimensions and half diameters of the edge finders don't need to be taken into account. All we have to do is find one edge, come up, set our reader to 0, move over to the other end, come down, come back and find the edge, look at the number, divide by 2, and come back to the middle of the part. Reset our 0, we're on the center.
Let's use the edge finder to find the center of a part. It's a very practical way of working, especially when parts are symmetrical about their center. So let's take a look at that. So let's start the spindle and lower it so that our edge finder can come in contact with the part. Not yet, but just at the right level. We're starting with the x-axis, so with the x-axis hand wheel, we're going to move the part so that it comes in contact with the edge finder. We're almost there. There's the movement that we're looking for, so that's the edge of our part. We're going to lift the tool after having set the x-axis to 0. Now we'll move over to the other end of the part. Note that we haven't taken any half diameters off or anything like that. Lower the tool and come and edge find the second end of that x-axis of the part. Right there, we look at the number, we don't set it to 0, and we see it's 3.194. So as we said, 3 inches, 194 thousandths divided by 2 will give us 1.597. So 1 inch, 597 thousandths of an inch. I'm now going to move my x-axis to get the readout to read 1 inch 597 thousandths. So there we are. We're now in the center of the part on the x-axis. If we start over those operations, but this time in the y-axis, well, then we'll be in the center of the part, very accurately in the center. Another way of edge finding, a very accurate way, is to use a dial indicator to edge find a part. It's a bit like what we saw with the centering of the part in the 4-jaw chuck, but with certain differences. The biggest difference being that this part, the outside surface of this part, has only one side to it. So what we're going to have to do is, with the dial indicator, come and indicate the outside surface of the part, and then project that surface. And what we're going to do is we're going to project it sideways because it becomes the vice jaw, and we're going to indicate the inside of the vice jaw, which is the same surface. When I do the end, well, I'll indicate that outside end, and then I'll abut a nice flat block onto it to project that surface upwards. Let's start by installing our dial indicator in the drill chuck and positioning the needle of the dial indicator slightly at an angle towards the surface that I want to indicate. Then, using my y-axis, I can position the dial indicator so that when I swipe the surface, I just barely touch it, only by a couple of thousandths of an inch. Then, by swiping the indicator back and forth, I'm going to find the high spot of contact between the dial indicator and the surface that I'm indicating. Once I've found it, I'm going to physically turn the dial to 0 at that very spot. So my high spot is 0. It's very important at this point to set my digital readout to 0 in the y-axis. I can now move my table so that the dial indicator is situated above an unused portion of the vice jaw. That portion is going to be the reflection of the side that I've already indicated. I can now turn the dial indicator in the spindle by 180 degrees and back up a little bit so that the dial clears the edge of the vice jaw. I can then lower the dial indicator and move the table in y-axis to come and rub the side of the vice jaw with the dial indicator. I can now pivot just slightly the dial indicator to find the high spot. And using the y-axis to adjust the dial, I can set it to the 0 that I had set on the dial when I indicated the first side of the part. And that means that the spindle is positioned evenly from the front and the back side of the surface. Since I set the y-axis to 0 when I was on the first side of the part, I can now see that the difference between the first and the second side of that same surface is 312 thousandths of an inch and 5/10. So 312 divided by 2 will give us 156 thousandths of an inch. And by using my y-axis, I can reposition the part to 156 thousandths of an inch, so halfway, and then reset my y-axis to 0. And that'll position the axis of the milling machine directly above the surface we were looking for. And we've done it by indicating the outside surface that we wanted and its opposite, which was the vice jaw.
All I have to do now is redo the same series of operations in my x-axis. Once I have the 0 in x and y, I'll have found my reference point. Now, another technique or method, the fourth, that we can use that uses, again, a dial indicator, well, is to use an edge finding square. Now, this method is quite accurate as long as it's used on an accurate part. So let's take a look at that.
It would be good to describe this very peculiar instrument. It has two flat surfaces that incorporate magnets. These surfaces are separated by precisely 90 degrees. These surfaces permit the very precise positioning of the part on the corner of a block. The tool also incorporates a very, very accurate hole that is positioned exactly so that its center is on the intersection of the two flat surfaces underneath. That means that when I position the tool on the corner of a part that's quite accurate and square, the part has to be accurate, and if I indicate the hole very accurately, the spindle's axis of rotation will be positioned directly above the intersection of the surfaces of the part. So I'm doing X and Y at the same time. We can start by positioning ourselves by eye as close as possible to the center of the hole. Just as in most accurate centering operations, we don't want to use the dial right off the bat. We start by centering by eye. When we're satisfied that we're getting close, we can move the dial indicator into the hole and continue with the visual centering of the axis. I'm getting closer, so I can give myself a little more sweep on my dial. I'm a little high on this end, so I'm going to move over just a bit in X. I'm getting closer to the center. Start checking around at 90 degrees, one check from the other. Give myself a little more sweep. Come back into the hole and verify again. So I'm off a little bit on this side. I'm going to have to move my X a little more. I'm getting close, but I'm a little high over here, so I'm going to move half the difference between the two sides. The same thing that we were doing when we were centering our parts in the four-jaw chuck. So I come over and check again. I'm getting close. Check here. I'm going to reset my dial to 0. Verify 0, 0, and 0. My spindle rotation is on my reference point.
Once my indicator reads 0, 0, well, I'm on center. And since the center of that hole that I'm indicating is exactly on the intersection of the two surfaces of the part, well, I've found my reference point. It's a little quicker than the other methods because I've done my X and my Y simultaneously, and there's nothing to take off or divide in two here. It's really the center point or the reference point of my two sides, X and Y. All I have to do now is zero out my readout, and I'm good to go. Now, we've seen four methods of edge finding that go from the least accurate, the touching off method, to the most accurate. Now, it's not always a good idea to use the most accurate method. Really, it'd be a waste of time and good tooling to use a very accurate edge finding on a part that's very rough and inaccurate. So it's up to you to choose the best method for the job that you're doing. And to everyone, happy machining.